Hi ladies and gentlemen, in this video we see the output of LTI systems, both continuous time and discrete time systems. The speech is organized in your learning outcomes, the impulse response of LTI systems, derivation of the output of a continuous time LTI system, output of a discrete time LTI system, and the summary of understanding. So your learning outcomes are you will learn the impulse response of a continuous time and discrete time LTI system. Then you will derive the outputs of CT and discrete LTI systems. Then you will understand discrete and continuous convolution on signals. Now the impulse response of an LTI system. An LTI system is fully characterized by its impulse response. The impulse response of a continuous time LTI system is it is a response to the system for a unit impulse signal at the input, that is the output yt when the input is xt is delta t. I have a continuous time LTI system that receives the input xt and the output is yt. Now what is that yt for which the input is delta t? That output is my impulse response. So likewise, if I have a discrete time LTI system, it's the impulse response of the discrete LTI system is the output yn when the input is xn is delta n. This picture represents it all. I have xt, this is a continuous time system with input xt and output is yt. Now this xt is replaced by delta t, then the output yt will be h of t. That is the impulse response of the system. It is characterized by h. It is usually denoted by h. Now I have a discrete time system to which the input is xn, output is yn. Now if this xn is replaced by delta n, the output will be hn. One can derive the general output. So here hn is the output of the system for the input delta n. So what if a general input xn or xt is given? So let us derive that. Output of a continuous time LTI system. So if the response to delta t is ht, what is the response to xt? Suppose I have a signal xt here, a continuous time signal xt here, and here I have a delta t here, delta t happening here. Response to delta t is ht. Okay. Now suppose this delta t is delayed by tau units and it appears here delta t minus tau. Okay, what will be the response to the response, because this is a time invariant system. So if I give a delayed input, the response will be equally delayed. So output will be output of this delta t minus tau will be ht minus tau. Okay, output of delta t minus tau will be ht minus tau. Output of delta t is ht. Output of delta t minus tau is ht minus tau. Why? Because the system is time invariant. Now this delta t minus tau has a height of 1 here, unity here. At that time the input is has a height of x tau, because this is my xt, input is x tau, this is the interval tau. So the height of this pulse will be x tau. So if the response to delta t minus tau is ht minus tau, what is the response to x tau? That will be x tau times ht minus tau, because this is a linear system. This is a linear system that obeys superposition. So the scaling applies. So this impulse has a height of 1. This has a response of ht minus tau. So if the impulse has a height of x tau, what will be the response? That will be x tau ht minus tau by linearity. So y tau will be x tau ht minus tau, since the system is linear. Now this position of tau can be anywhere. I can place this tau anywhere and integrate for finding the total response. So the total response yt will be minus infinity to infinity x tau ht minus tau d tau. So that is minus infinity. It's the same as minus infinity to infinity h tau xt minus tau d tau. So this operation, this integral is called the convolution integral. This is a famous convolution integral. Now you can see that if the input to an LTI system with impulse response ht is xt, the output is yt will be xt convolution ht. That is the same as the that's the same as the response of a system whose impulse response is xt and the input is ht. These two equations are the same. Okay. So this is a convolution integral. Now likewise, if I have a discrete time LTI system, response to delta n is hn. So I have delta n happening here. Okay, I have a delta n here at n equal to 0. So delta n has a response hn. So if this is delayed by m units delta n minus m, the output will be hn minus m, because this is an LTI system. It's a time invariant system. So response to delta n minus m will be hn minus m. Now this pulse has a height of xm. This impulse has a height of xm. This is my discrete input xn. These blue signals. The dots are my input. So this input has a height of xm there. So the response to xm will be xm hn minus m. xm hn minus m. Now the position of m, this can be anywhere from minus infinity to infinity at any discrete interval. So here I have total response output will be minus infinity to infinity xm hn minus m. That is same as minus infinity to infinity m from minus infinity to infinity hm xn minus m. This is summation is in m. Final sum is in n. So yn is m equal to minus infinity to infinity hm xn minus m. This operation is the discrete convolution sum. This is a discrete convolution sum. In the continuous time case, it's a convolution integral. This is a convolution sum. Now coming to the summary of understanding, you understood the impulse response of a continuous time and discrete LTI systems. Then you derive the outputs of a continuous time and discrete LTI system. For continuous time LTI system, the output is yt is minus infinity to infinity integral h to xt minus tau d tau. That is a convolution integral. For the LTI discrete system, the output yn will be some sigma m from minus infinity to infinity hm xn minus m. So that's a convolution sum. Then you understood the discrete and continuous convolution on signals. And that is the end of this presentation. Thank you all.